Good afternoon, ladies and gentlemen. Welcome. The topic of today is feature engineering. And this is a very interesting, a very creative, and a very important step in designing a machine learning tool chain. And we will especially look at two kinds of data: text data and audio data. Speech, sound, and then also text. This makes a big part, a big quantity of today's data is in text, is in sound. Of course, there are more pictures even, but it's amazing how much data is created. I think more than 80% of the data worldwide, digital data, was created in the last 2 years. The rest is older than that. Before we start, let's make a short wrap-up of what we learned last week, not yesterday. Best practices. How do you tune a learner? The idea is here, start simple, start low, and then advance to more sophisticated, more complicated learners, but start with a rather high bias learner, and then continuously or stepwise add complexity. Tune the hyperparameters. So that you can see, okay, what is the bias variance trade-off? Then increase the number of features, plot always learning curves. The learning curve is the plot of the test and training error as function of the training size, or the test size. And from these curves, whether they converge at a high level or low level, and from the difference of these curves, you can judge whether this learner is a high bias or suffers from high bias or high variance. Use always cross-validation. Means that make use of your test or your training data efficiently. Split them up, for example, in 5 subgroups. Use 5-fold cross-validation to get an average of the performance over these sets. Never just try one, because these performance measures are also statistical measures. They're random variables, so we have to train more than once to get an estimate about the distribution of these parameters. Grid search is used actually for tuning the hyperparameters in the inner loop. And it's mainly actually a for loop or a nested for loop through all the parameters that you give from outside to the learner, which are not a priori defined, such as, for example, the number of nearest neighbors for a KNN classifier, or which kind of metrics is used to measure the distance or the similarity between two sample points. Regularization is a special means to select features, and this will be a topic of today. Especially lasso regression, which uses the L1 norm. This is the norm which uses the absolute value of the components of a vector. L1 norm is good at selecting relevant features. Especially if you have a linear model, try L1 regularization to skip out some features, because normally we have too many features, and a learner normally can suffer from overfit, from high variance problems. If more data is needed, either you can create more of this data. Especially this is simple by, for example, the data we look at now, audio data or image data. You can just shift pictures, you can flip them, you can change the grayscale values, you can change the gamma values, you can add noise. At the same thing you can do at audio data, and without the need of taking new data, you can generate 5 times the data you have. And using all this data makes the learners much more robust. What is covariate shift? The idea behind that is, at the time when you train the learner and evaluated it, it might be that this statistical distribution of your input features was such and such, and this one can shift, it can change. For example, If you think of a Gaussian distribution, the mean could shift a little bit, the variance could get bigger and bigger, and this normally happens with non-stationary processes where things are flowing away, drifting away. And for this, actually, you could use two development sets. Development sets are also called validation sets within the cross-validation. So that you say, I have a validation set which is closer at the time now, at the time where we actually want to deploy that learner, and another one which uses old data. And then you can assign, or you can check how big this variance shift is. So take actual data, take up-to-date data. This is very important if you have non-stationary processes. Good. What do we want to learn today? Before you start training a learner, we should always look at the data, and we should look thoroughly into it, like a detective. It's a detective work to get most out of the data, and this is mainly manual work because you have to use really your brain. It's called EDA, Exploratory Data Analysis. So it's like you're an explorer, you're an adventurer. You look in the data without prejudices, without having anything in mind, just open to discover things that you probably don't think that they're in. What then we have to do is preparation, bringing the data into a nice format, and this is also called, like a spreadsheet format, I would say. It's the third normal form of this data, and we have to apply cleaning to get the rubbish out, because the rubbish could really disturb. We will see this, especially in text data. We have to pick out a lot of rubbish, which is not helpful. Feature engineering means also, generate features, which are necessary, which are helpful, and at the end probably also kicking out features that are not helping. So this is feature generation and feature selection. These are two processes which follow then. And here we look at four methods how to select features. One thing we had already, the lasso regression, and we have univariate feature selection. This is mainly looking at the correlation coefficients in a linear model for one feature after each other, so single feature, single feature, single feature. Or tree-based feature selection. This is a very nice one because it looks at all features in common together and takes out the most relevant ones, and you get a kind of a feature relevance indicator out of a decision tree. And then there's another method. The idea with recursive feature elimination is that you kick out the worst at the beginning, you train again, you kick out the next worst, and start again. So this is called recursive feature elimination. Then we look at especially two types of data, as I said, audio data and text data. I will just explain how do you bring text data actually in a data format that you could use for training, a classifier, for example. Text classifier used for sentiment analysis if you want to see, and if you want to grab through all the Twitter messages about Donald Trump or so, you could make kind of a classifier about these Twitter messages, whether it's well for him or not. This would be an idea. Okay, this is the ideal world. We generate features, train a model, deploy it, sell it, whatever, and make predictions, but at the end we make money. But the world is not normally so simple, because a lot of work is here in how you generate features, how you sell it. And there are people saying that it's even the most important part of machine learning, because you bring in, at this point, actually your expert know-how, your expert knowledge, your a priori distribution of things by already selecting relevant features. What is a feature? I would call it, or Christopher Bishop calls it, it's an individual measurable property, so it's measurable, of a phenomenon being observed. So it's a real observation, or deduced from an observation, but it must be measurable. So you can repeat it, and it will give more or less the same answer. If you measure twice, then you get the same thing. Here are some voices from some machine learners about feature engineering. coming up with features is difficult, time-consuming, requires expert knowledge, but it's good actually. A learner needs expert knowledge. And applying machine learning is basically feature engineering. This is Andrew N. from Stanford University, he's very famous actually machine learner. So he says, this is a lot of work. You really have to crank your arms and work. Feature engineering is the process of transforming raw data into features that better represent underlying problems to the predictive model, resulting in improved model accuracy on unseen data. So it's actually the way to reduce also actually the degrees of freedom of the input data so that the learner doesn't overfit. To keep actually the variance of the learner. We get the most relevant things in, and all the things that don't contribute, we kick out. Luca Massaro says, the features you use influence more than everything else the result. No algorithm alone, to my knowledge, can supplement the information gain given by the correct feature engineering. This is probably also a discussion we could lead, because there's one reason I didn't put images as data source for our classifiers, for example, because there mainly features are generated by a convolutional neural network itself. So the network is there to first of all generate the features. And 5-10 years ago, actually, there were also methods to generate feature vectors out of the images, not using convolutional neural networks, for example, histogram of oriented gradients and so on, but I think they're less and less used because these convolutional networks per se find actually features which are relevant for the task. Needs a lot of training. They do actually for the first layers, it's just feature engineering. And then later you have fully connected networks, they decide, they make the classification, whatever. Good. When we start a machine learning project, actually we have a kind of a life cycle. It starts with collecting data. No, it starts further. It starts with thinking about what do I want to achieve? What is the goal? What is the necessary accuracy needed? What are my hypotheses? What is the prejudice that I put in, or the preconditions? And how do I measure success? This we should think of at the beginning, before we start collecting data. Just to have a clear goal and say what is needed, and how do I measure success? And then we would start gathering data, cleaning the data, bringing it to the right form, looking at the data, and then we can start doing the learning task. So this is only a small part of it. And there's even a process defined, I think, by IBM, which defines this, like an ISO process and so on. Which steps you have to go and so on. I don't bring it here. I think this is clear enough, and it's also, how do you say, it's natural thinking. That's how we would do it. So the ideal world would look like this on top, but normally it's a mess here. We have different data, taken at different times with different sampling rates in different formats, and we have to gather data from different files together and collect them together. This is already a lot of work. So we have to get rid of all this junk and generate a nice table of features which we can work from. And then we stand in front of the task of generating meaningful features. And this is what we're going to look at today. Okay, this is actually now the content of the process we looked at before. Feature generation, feature selection, and then we look in text data and sound data. How does it look there? What are the features for text? Or what are possible features in text? Feature generation starts at the beginning, for example, if we have to encode categorical variables into numerical ones, or into one-hot encoding variables. One-hot means 0 everywhere. There's just one transistor which switches on the hot one which says, now it's this class, for example. And there's only one of this class, and all the other classes are in a multi-class classifications are 0. It's better than using, for example, class 1 to 9, because in these labels 1 to 9 there is an order. There's a numerical order, and you will conclude, okay, class 9 is higher than 8, but it's not. They're the same actually. They have the same rights, or they're the same level. And so it's better to use a one-hot encoding in this case, because otherwise you could think of a trend, Of course, there are some ordinal data, like for example the star rating in a film, which has this ordinality, so you can keep it. Or the degree of an official, how many stripes does he have? Does he observe or desert that? Good, okay. Exploratory data. By doing this, we can often discover important anomalies, and we shouldn't discard these anomalies. I think this is the big success and the big advantage of machine learning compared to other methods where you think of physical modeling. Physical modeling would skip these unimportant things and say, let's reduce to the model where we can treat it. But sometimes it's especially these outliers that help us to really, in a special situation, correctly classify a task, for example. And we should understand where these anomalies come from, whether they're really generated from the process we want to look at, or whether they're now from some excessive noise where we're not interested. So these anomalies, like a black swan, which is very rare, but it's there, it could be useful. We should also look at limitations of our collection process. For example, if you look at trading data and you see, okay, the trading house was closed over weekend, you cannot do any predictions there. Like, for example, the Swiss stock exchange wouldn't work there, or on holiday days. So you have to think about how do you treat this missing data in a time series, for example. Can I fill it up? Should I skip it? You have to think about this. Or limitation of the collection process, that there are some missing data. For example, if the data stream is just too slow that you can feed, for example, the storage, it will just fill with some zeros or nans that are not there. And better info about this idea about how do I deal with this data. And what are the tools for doing exploratory data analysis? I would say it's plotting. It's really visualizing, because I think we as humans are quite visual. We're good at it, at looking at correlations in a scatter plot. If I just see these scattered dots, I would see immediately what kind of relations there is in between the independent variable, or one variable, one feature, and the other one. So histograms are good. That you look at the distribution of each individual feature. You look at scatter matrices, which plots actually correlation of one feature versus another. They can be huge, but they're easily generated. For example, using Seaborn, it's really nice. Do you know what QQ plots are? QQ, quantile plots. They're used for? Yeah?
To see if the data is normally distributed.
Right. So if you take the reference distribution to be a normal distribution, you could check for another distribution, is it also normally distributed? But in principle, you could use a QQ plot for any distribution. You can check, is it the same as this one? And it's just that you can put actually a reference distribution and check, is this also distributed like that? And you would see a straight line if they are, and you would see actually steps in the QQ plot, so non-continuous forms of this graph, if the Q's, so the quantiles are different and distributed. Heat maps, they're also good, especially if you want to if you generate pivoting tables, we will look at that. For example, if you pop one feature versus another, and you put the output given that one. This could be on one side. Yeah, we'll look at the heat maps, give a good one. Or also you could plot actually correlation matrix as a heat map, and then you would discover highly correlated features because they have a high Pearson coefficient, correlation coefficient up to 0.98, and then you know, okay, for linear models have to take care because they're highly collinear, they're correlated, and this might not be good for manual. Here is Mr. Tottier, a very famous scientist or statistician, and he says, EDA is like detective work. You have to go and be open for everything, like a discoverer, an adventurer, and look into the data and be open to discover new things which you didn't think they're in. So you have to go actually with open eyes, without a prejudice, just say, okay, let the data speak. It's not any transformation yet, just look at the data. Or Heather Hinman said, do not ever, I mean ever, in big letters, underestimate the power of good data preparation. That number one mistake that modelers make is related to lousy or totally absent data preparation. Good data preparation includes cleaning, transforming, and aggregating data. Aggregating means actually that you can sum, for example, or build a mean over a group of features. This means aggregating, and also how to treat that. The main message here is, if you feed into a learner garbage in, you will get garbage out. This is just to summarize the whole thing in a few words. Right? Okay, probably you've heard of these expressions. Data cleaning means actually homogenize the data. How to treat missing values of different type. We have to fix input error types and so on. This would be data cleaning, the first step. Then we go and look into the EDA by aggregating data. Let's say, let's look at the mean of something versus the mean of some other thing, or what happens given that class. For example, look at the Titanic data set. It's, probably know that. You could look at, okay, what is the probability you could already calculate that I survive given that I am in class 1, 2, or 3. You can make a plot, and then you could already conclude, okay, there's a difference. There's a significant difference for the survival probability or rate depending on the class, depending on the price I paid for the journey. Imputation of missing values means sometimes we have nans in the data. So they were just not measured, for example, and often, and this is not good practice, these missing values are filled with zeros. And from these zeros, you don't know whether this zero was measured or not. But you often see, if you plot the histogram and you see a peak at the zeros, that something like that must have been happened. That somebody filled things that he didn't measure just with zeros. And there it's difficult, because if 0 is a valid value in the data range of that feature, you cannot separate anymore which one were really not measured and which were really 0. So it's better to use something like a NAND, an np.NAND, to specify a thing that was not really measured. And often it can be that for one feature, half of the data that you have has a NAND. Because, for example, if you make a questionnaire, people are not willing to fill out everything because it costs time, or probably things not necessary. And then probably you would say, okay, you have to decide, do I skip the data, or do I impute some reasonable value? Imputing means assuming kind of, or imputing a value, or assigning a value given the other features, for example. The easiest thing of imputation is imputation by mean or median. Then you look at all other values within the feature column and say, all missing values are just filled by the median or the mean of the column of all the features. This would be a mean or median imputation. But you could also use something more sophisticated if you say, no, this is too simple. I just cannot replace a NAND by the mean of the column. Then you can say, is there a model behind it? Could I use also the other features, column 2, 3, feature 5, 6, 8, to generate a model that predicts this feature x1, for example. And then you would replace, after you have taught this model, actually, all missing values by the predicted value of the model for this column. So you place within a model, in your input data, using a model based on the other features, some values of a given feature, where you have a lot of missing data. This is also imputation using a model. And then, of course, you can also take into account correlations between some features. Binarization or binning is the transformation of discrete or continuous numeric features into binary features. That's binarization. Or binning, if you have continuous variables but you want to generate some classes, this is binning. For example, if you have the age of a person, okay? And you say, I don't want to predict the exact age of that person, because important for my task is it younger than 18, is it middle-aged, or is it older than 65? Then you can generate 5 bins, 5 classes, and you would bin then all the ages into these 3 classes, and the task is no longer to make a regression for the age, but rather a classification for this lifetime period. This is actually binning. And of course, using binning, you can reduce actually the dimensionality of the output or the input, both sides. And this helps because you're aggregating within a bin a lot of data, and you put them into the same box, which makes it easier for the classifier, for the learner to adapt. Sometimes the data is not evenly distributed. That's normally the case. For example, if you wait for a bus, the waiting times, they're not distributed, for example, uniformly, but they're distributed like a exponential distribution. So actually applying there a log transformation would even out these classes. Or if you have some highly nonlinear response, which looks like an exponential curve, and it also makes sense to first apply a log, and then, for example, work on the dB scale instead of the voltage scale. This would actually be that one, because there probably a lot of things are linear. Scaling and normalization is an important step for many learners, not for all. For decision tree, for example, it does not matter. But if you apply a KNN to not normalize data, you have a problem because they measure the distance to all other points. And if one dimension is not scaled, and it measures things in meters, and the other one, so in thousands of meters, and the other one is another measure in the interval 0, 1, you see that the weight of this one dimension is much, much more in the decision whether this is a neighbor or not. So this is important that you normalize it, scale it. Interaction features are, for example, especially if you say, I have some independent input variables as features, but if I make a linear model out of them, I cannot predict all the things my model or all my measurements would show. So you can combine features to generate interaction features. If you have a feature x1, a feature x2, you can multiply them to get an interaction feature between x1 and x2. Or you can create an interaction feature between the feature itself, so you have an x1 squared. It's like a polynomial feature for a general feature class. Good, okay. Here I just give some hints for those, just as a reminder in Python how to use or how to apply data cleaning. For example, Pandas itself, Pandas is a nice library for data preparation, for data visualization as well, for EDA itself. And you have methods here that drop the duplicates, that drop lengths, or that you can use, for example, to replace something where you don't have an entry. A very nice method here is group by. So you can generate actually aggregated features, grouped by, for example, sex, and then you have female, male, and you can look at the data from this perspective. Grouped by, for example, class in the Titanic work. And then you see, okay, now all entries are aggregated by this class, and you will get a table, sometimes a multi-index table where you have the entry and then the class, and then all other features which are aggregated, for example, by the sum or the mean. Here, after a group by, you normally have an aggregate function which says, okay, what shall I do with the data I collected together by grouping all the weekdays? We will look at this kind of grouping in one of the exercises after the lesson here. For example, many things depend on the weekday itself, so that we have things which are more frequent on the weekends or Friday night. And then this is an important feature, and you look just at the Friday nights. What happens at Friday nights compared to Tuesday nights, for example? Then you learn what these data tell you. I don't know whether you know this apply function in the pandas to transform data. We can use a lambda function. So this one takes a string and replaces a star by an empty string, so it takes it out. Or this is a very nice format. If you don't know the date time format, it's a kind of a normed, very universal format to be used with date time, so for its time series. It's very mighty. It's very powerful. For example, to select out all Friday nights. It's easy to group everything by an hour, for example. Then it aggregates every data, sums it and bins it into the hours, and sums it up. Date time format here. Okay, pivot tables. They're used actually. For example, this is an example of a multi-index column. Also very helpful when doing EDA. Normally in a pandas data frame you have only one index here, the standard index, but you can make grouped multi-indexes so that you can say, okay, this is the upper class and lower group, and so on. You can generate multi-index tables which help you actually to analyze in detail what happens using a pivot table. And as long as you give here two arguments for the index, it makes automatically actually a multi-index pivot table with aggregated features over these indexes. And you have to apply an aggregation function. Here it's the mean, but you could also define an aggregation function for yourself and give it as argument to this pivot table. Good. What do we have? Missing values. Here we generate just one with missing values, and we use the fill NAND to replace it by the mean of this feature. And you see here the mean of 3, 4, 2, 3. And these NANDs are replaced, and this is an important argument. If you put in place equals true, the whole data frame will be replaced, and you no longer have access to the old one. So it's a new one. You no longer have the columns you had probably. It's probably a little bit dangerous, but it's also very practical if you use that in place equals true. Good. Let's look. What do we do if we have data that is skewed? Skew means in German it's schief. If the histogram, if you plot the histogram, it's not symmetric around the mean. But there's an asymmetry. And this asymmetry is measured by the skewness, which is actually the third statistical moment, so the third power. It's not a variance. The variance is symmetric here. It's the third, so it weights things which are higher than the mean and lower than the mean with different signs. And you get down to skewness. And already an NP array has actually already the method skew. So from every number column, you can immediately calculate the skewness. And it's often also good to equilibrate that skewness, to bring it to zero, that you have a histogram which looks more like a normal distribution. And this is done using either that Box-Cox transformation. No, it's a power transformation which makes this uneven distribution more even. And the lambda is optimized automatically to bring the skewness to 0. This Box-Cox transformation is normally only defined for positive data, but there are generalizations of this Box-Cox transformation, which are called the Yale-Johnson transformation, which also work for negative data. And that's how it looks like, for example. This is data from the low carbon data. We look at weather data. The low carbon data is measured in UK, where they measured, I think, 570 households over years, the power consumption, and tried to correlate it with the weather. And the idea was, can I deduce from the power consumption of a household who lives in it, to which class this family belongs? Is there something like that? And here you see skewed data. It's a long tail on the right side, and after applying Yale-Johnson transformation, you get a histogram which is really similar. This can help. One-hot encoding, bin counting, label encoding. I just put here some snippets probably you can use. One-hot encoder is already implemented in scikit-learn, and you can, for example, with your strings here, or nominal features, you can assign them some values. 1, 2, 3, whatever you like. Bin counting and label encoding here. The label encoder does it automatically, just selects a number given. So it looks at the number of non-unique features or unique features, yeah, and gives the number automatically. This is the label encoder. And from now on, you don't have actually Paris and Tokyo or Amsterdam as features, but just 2 to 1. And the assignment, you can reverse it to get it back. So there's an inverse transformation for this one or the label. Okay. Yeah, let's start with text analysis. Then after the break, we do the sound analysis. Who has already worked with text data? Yes. Can you tell something about that? What did you do?
We have a text data analysis course this semester.
Okay, so this is
So
treated there.
tokenizing, normalizing, you are familiar with this.
So is everybody familiar with
I
that?
think it's not.
Who has never done text transformations? So I think I'd bring it short, it's okay? Yeah? Then we have some experts here that can explain it even better. But I just bring the main idea. Good. Tokenizing means actually splitting, for example, a sentence into different entities like words, tokenizing, that you can work on. Sometimes this makes sense. Sometimes it's better to look at the full sentence because with speech, with text, actually we have normally a conditional dependence along the line. They're not independent, the words, the objects, and so on. But let's say we ignore these ones. This is already a decision we make and say, okay, let's ignore this, for example, temper or causal or grammatical dependency of the words in the sentence. We tokenize it. And for each token, we give an integer. Using white spaces and punctuation as token separators, this would be the normal case. We count it and normalize the weighting with diminishing importance tokens that occur in the majority of samples and documents. We look at that in detail. Okay, tokenization. So we group the full text. Common separators, operators, punctuations, and non-printable characters are automatically removed because they don't help, for example, in a sentiment analysis. Sometimes they help if, for example, 10 hyphens are added once or 5 smileys and so on. You should also look at that. So you can treat these as well. And often we have stop words. And we want to skip those stop words. So very, very frequent words like is or that or the. and we don't use those. We want to skip them because they just fill up our dictionary of words that we have. Then we apply stemming or lemmatization. Stemming is actually reducing the words to the root of the word. And stemming is a little bit more primitive than lemmatization because it does it actually by cutting the ends off, for example. Let's say like daily would reduce to day. Or what could you say? Yeah. Normally the stem is like the trunk of a tree and it reduces to the root of this word. And lemmatization is more sophisticated. It really looks at the meaning of the word. It reduces it to the correct root of the word. So there's a whole actually vocabulary behind the lemmatizer, which says, okay, for example, it would even reduce a tome, which is another word for a book, to a book. So it uses even synonyms to reduce it to the same one root synonym. And then you can just, let's say, the things which mean the same are also represented by the same root. There's a powerful toolkit in Scikit-learn, or no, NLTK, it's a separate toolkit, Natural Language Toolkit, open source, and it supplies all these operators for doing lemmatization, stemming, or tokenization. And I mentioned here another thing. This one, the reg module or the regex module. Somebody heard of that already? Regular expression. This is a really sophisticated module to deal with text data. And it has many rules which can be, here you kind of cryptically could deal, and it transforms the text in a very nice fashion. But you have to learn the syntax first. A to Z, small letters, big letters. This is a class of what it does. So you have to really work with it to use it. It's quite mighty. Let's look at it. So, a text data could look like that. And of course, there's a lot of chunk in, and we have to clean it. So we have to get the backslash away. We have to get, for example, the numbers away. This is what we can do with regex, for example. We take words like is and it away, the. These are the stop words which are not necessary. And things like that here. Approval is not separated by 48. By 48 we take away. And do we see some stemming here? Not yet. The president. So the words are the same at the moment. No stemming applied here. But here it looks quite clean now. And this is a nice thing to work with. And we can continue. Okay. Now let's see what stemming or lemmatization does. In NLTK, there's called the porter stemmer, which reduces all these words to the root of the word. And there's also a lemmatizer here. WordNet lemmatizer, which is really mighty here. The love to heard, so it takes also the time, puts into the present time, from heard gets to hear. Word, it's skipped now. Triggered is the infinitive, to trigger, it's replaced by at one. Memorizes, to memory, or to memorize. High, exit, move, beast. And so you have reduced it actually to the same root of the words, to the same time even. There's no past time anymore. Okay, this is the example. It's quite astonishing. So a tone gets your book, and then you can say, okay, it's the same word, it's a synonym, it's replaced by one of these synonyms. Yeah.
The first word, the shouldn't it be reduced?
Right. Yeah. So
because it's cutting off by and off and yes.
No,
well, so
yes. Normally it would be a stop word. It would get out. Right. So I have to try it out whether this remains. I think without skipping the stop words first, it probably would keep it. But the bar is gone and the off. Yeah. Now, if you have actually done this, we can hash this text. Hashtag, you've heard about it. Hashing comes actually from information technology that you give something an address code actually, so that you know where it's stored and you have immediate access to the data that you look for. And the idea of hashing is similarly, you give something a code and you immediately say, okay, using this code I can even, like in a library, know on what shelf this book is. And this you can do also with the words you have. You could hash them in the vocabulary. And there are hashers here, which do it very, very intelligent, which really take the meaning of the word and place words which are close together by the meaning, close together by the numbers. So you have a representation in integer numbers of certain words, which gives even actually the similarity of the words in the number itself. That's hashing actually. And at the end you have actually a dictionary of the words which is represented just by numbers, and you know which number means what class of words or what root of words. And then you have numbers and you no longer have text data. That's called the hash. Okay? And yeah, how do you select this one? Hashing, yeah. There are also now pre-trained models that you could use. There's something like a word-to-vec, which is trained using huge neural networks which assign to a word a number, a vector, or a vector of numbers, with many dimensions. And this